Hello learners. Let's start with a simple puzzle. Have you ever tried pushing down on a syringe that has no needle attached? As you press harder, the air inside squeezes into a smaller space. Why does this happen? Well, in the 17th century, Robert Boyle was just as curious. He studied how gases behave when pressure is applied and temperature is kept constant. He noticed that the volume of a fixed mass of gas decreases as the pressure increases. In fact, if you double the pressure, the volume is reduced to exactly half. Pretty neat, right? This behavior became so famous that it was named Boyle's law after him. Boyle basically turned the squishy nature of gases into a scientific rule. Now let's state the law clearly. Boyle's law says when temperature remains constant, the volume of a given mass of gas is inversely proportional to its pressure. That means volume is proportional to 1 divided by pressure. In short form, V is proportional to 1 over P. Putting it mathematically, pressure times volume equals a constant. Here, V stands for volume, P stands for pressure, and K is the proportionality constant. But remember, this only works when the temperature is unchanged. So if pressure doubles, the volume becomes half, and if pressure is halved, the volume doubles. It's like a seesaw balance between pressure and volume. Let us now derive the useful formula. Consider a fixed mass of gas at constant temperature. Initially, it has pressure P1 and volume V1. Later, if conditions change to pressure P2 and volume V2, Boyle's law tells us P1 multiplied by V1 equals P2 multiplied by V2, that is P₁V₁ equals P₂V₂. This equation is the working form we use in calculations. So whenever you see a gas problem with pressure and volume changing while temperature is fixed, immediately think of this golden formula. Of course, no law is accepted in science without experimental proof. To test Boyle's law, a fixed mass of gas is trapped in a closed cylinder and pressure is increased using a mercury column. As the pressure increases, the volume of gas is measured. The data is fascinating. At 1 atmosphere, the volume is 1000 milliliters. At 2 atmospheres, it shrinks to 500 milliliters, and at 4 atmospheres, it reduces to 250 milliliters. If you multiply pressure and volume in each case, you always get the same value, 1000. This confirms that pressure times volume is constant when temperature is fixed. Let's visualize it. When we plot pressure on the x-axis and volume on the y-axis, the curve is a smooth hyperbola. It shows that as pressure rises, volume falls. If instead we plot pressure against 1 divided by volume, we get a straight line passing through the origin. Both graphs confirm the inverse relation between P and V. These curves are called isotherms because the temperature is held constant during the process. So the next time you see a hyperbola in your gas law graph, remember it's Boyle's signature curve. Now let's solve a problem together. A gas expands from 300 milliliters to 1800 milliliters at constant temperature. At the end of the expansion, its pressure is found to be 1 atmosphere. What was the initial pressure? Let's apply the formula. P₁V₁ equals P₂V₂. That means P1 multiplied by 300 equals 1 multiplied by 1800. Rearranging, P1 equals 1800 divided by 300, which gives 6 atmospheres. So the initial pressure of the gas was 6 atmospheres. Isn't that simple? Just plug in values, keep units consistent, and you're done. Finally, let's see where Boyle's law shows up in real life. Think of a syringe. When you pull the plunger, the pressure inside decreases and fluid is drawn in. Boyle's law at work. In scuba diving tanks, air is compressed at high pressure to occupy less volume, making it portable. Vacuum pumps use the same principle to suck air out of containers. Even balloons shrink when taken to deep sea because the external pressure is much higher. And of course, Boyle's law is a stepping stone to the grand equation of gases, PV equals nRT. So, to wrap it up, Boyle's law is all about the beautiful dance between pressure and volume at constant temperature. Increase one, and the other must decrease. From syringes to scuba gear, this law is quietly at work around us. I hope this session helped you see that gases aren't just invisible. They are obedient, playful, and mathematically predictable. Catch you in the next class, where more chemistry adventures await.